Oh, I just did it.
Here we go. You can go
Okay.
ahead.
Yeah, my name's Ivan Rodriguez. I'm the Technical Programs Director for the Canada chapter. And tonight we have Ivan Taylor joining us for yet another webinar. So Ivan has provided quite a number of webinars for the INCOSE Canada chapter and also for other chapters, working groups, the social systems and resilient systems working groups. Ivan has presented multiple times at the INCOSE International Workshop and International Symposium. Ivan is the president and senior researcher at Policy Dynamics. He has a master's degree in uh, in information and system science and a PhD in public policy. Um, Ivan's been a member of the Canada chapter board for, I think, 3 years now, going on 3 years. A very active member and contributor to this Canada chapter. So thank you very much for all of your involvement and participation, Ivan. I am very much looking forward to this presentation. I was telling Ivan as we were just getting things started and waiting for some people to join that my son even has been he's very environmentally conscious, and he's been hounding me about the how we're impacting our environment with AI indirectly, and we don't really see what's going on under the hood. I don't know if that's something that you're going to be getting into, Ivan, but let's turn it over to you. The session is being recorded. You'll find it on the INCOSE Canada chapter website if you want to view it or share it sometime after the presentation. Usually takes us a day or two to get it up on the site. But with that, take it away, Ivan. Looking forward to this one.
Yeah, thanks, Ivan. Yeah, just a comment I saw in the chat from Kai that I am also an active member of the Sustainability Working Group in INCOSE. And I've titled this presentation Operationalizing Systems Engineering for Large Language Model Sustainability. So I have two co-authors. This is a paper we're hoping to publish. And I have two co-authors, Vinitash Mishra from the Arab Emirates and Suraj Kul from India. So yeah, as I said, this is a paper that hopefully will get published somewhere eventually. So I'm going to give a little summary at the beginnings, basically tell you what I'm going to tell you before I tell you, and that'll hopefully whet your interest to see how it's going to pan out. Then I'm going to talk about system dynamics. I don't know if Ivan Rodriguez mentioned it, but my specialty is system dynamics, and policy dynamics specializes in system dynamics. So I'm the senior researcher in policy dynamics, specializing in system dynamics. And I think system dynamics and systems engineering has a very close relationship. So that's why I often do presentations on system dynamics. So in the system dynamics part of the presentation, I'll talk about the problem and scope, and I'll talk about the model we built in system dynamics and the calibration and the governance ideas, so the policies we developed. And basically the policies we developed were two levers that we can pull to try to reduce emissions from LLMs, and they are energy efficiency and the use of renewables. And then I'll get into systems engineering and how we can take the results from the system dynamics models and turn them into actionable projects in the systems engineering environment. And so I'll talk about the goals and scope of the projects that we are defining, and then how we'll measure success. And then I'll talk about the risks mitigation and the owners of the projects, and then hopefully you'll see how we can mix or use system dynamics and systems engineering to make a common framework for, as we all want to do, make the world a better place. So as an executive summary, I'm going to show you a system dynamics-based CO2 model for large language model operations. And in the baseline case, the long-term equilibrium value is that large language models, at least the one we looked at, ChatGPT, could produce up to 42 megatons of carbon dioxide a month. And just to put that in perspective, that's 60% more than is produced by all of Canada today. And we have two approaches, well, not two approaches, but two sort of scales of activity. The first one is a moderate sort of activity that could be implemented maybe more easily, and an aggressive activity that may require more effort. And we have the two ideas, basically efficiency gains by investing in research and development to make the algorithms and the hardware more energy efficient, and then use of renewables and the adoption of renewable energy in the energy use from the LLMs. And the output is what I hope will be a traceable system dynamic systems engineering blueprint for sustainability of the LLMs. The problem statement and the scope. First of all, we all know that the LLMs are growing, use is growing exponentially, and as they grow exponentially, they require more and more computing power, and with more and more computing power, they require more and more electricity, and with more electricity, they create more carbon dioxide, and it's growing exponentially. And then, so the scope is that this project, we only looked at inference in terms of queries in ChatGPT, actually. So we calibrated the model to ChatGPT data, and we only looked at inference. We didn't look at training requirements or training energy usage. We only looked at inference, that is, queries that are user-defined queries for ChatGPT. And the objective, obviously, was to cut the CO2 emissions per kilowatt hour per query without hurting user value or service quality. And the decisions that we hope to make is to develop product roadmaps and use data center siting and energy sourcing, and finding ways to invest in R&D for efficiency gains in query energy. Okay, so here's ChatGPT data. So this is the number of visits to ChatGPT for the last, up until the end of 2024. And you can see the actual visits in blue. And I really can't explain what happened here in 2024. I don't know what I haven't found any way that explains that. But anyways, the model that we calibrated is shown in orange, and you can see that we got a reasonable fit to the data. And then you can see, obviously, that the real important part is this last tail of the data, which shows this exponential growth. And so we have, as we have early adopters, and then we have a saturation of the early adopters, and now we're getting into the later adopters, and basically we're growing exponentially since 2024. Okay, here's the dynamic hypothesis, which is basically a feedback look at how these processes work. And I'm not sure if you're familiar with feedback loops and things like that, but this is basically reinforcing and balancing loops. So a reinforcing loop means that it leads to exponential growth. So here we have active users that have successful implementation, which encourages new users, which increases the active users, and then we go around this loop, growing at a reinforcing and exponential rate. And then we have another reinforcing loop, which is integration in the workflow, which creates more queries per user, which creates more queries, which creates more successful implementation, which creates more integration in the workflow, and that leads to another reinforcing loop of exponential growth in the number of queries created by the integration in the workflow and the successful implementation of AI. And then we have some balancing loops, and the balancing loops are interesting because they try to control the reinforcing loops. So basically, exponential growth can't go on forever. So we have to figure out ways to somehow control it. So we have some balancing loops. The first balancing loop, this B1 over here, is the potential of market saturation. So we have total users and market saturation. That reduces the potential users, and then that reduces the new users. So this is a balancing loop of market saturation. And then the second loop over here is cognitive load. That is, there's only so many queries that a person can actually handle. So there's a cognitive load on the user, and there's a cognitive capacity of the user, and that limits the number of queries a user would do in a month or a day or whatever. So that's another balancing loop, similar to saturation, except this is like mental saturation. And then here we have some other balancing loops, and this first one is the energy consumption loop, which basically says that computational requirements will increase the energy consumption, and then through technological advancements we can reduce the computational requirements. And one of the things we note here, which isn't shown in this diagram but probably should be, is that more energy consumption leads to more pressure to reduce energy consumption. So that energy consumption comes at a cost, and as the cost rises, there's efforts to reduce the consumption and reduce the costs. And here is another balancing loop, which is the push towards renewables, that more emissions means the more of a push towards renewable and nuclear energy, and the share of energy produced by fossil fuels goes down, and that leads to less emissions. So this is another balancing loop that may come into play to reduce the emissions. And of course, what we're interested in is the energy consumption and the emissions created by that energy consumption. Here's the system dynamics model. You can't read it, unfortunately, but let me just show you, just tell you what these things are. This over here is a stock of potential ChatGPT users. This is the actual ChatGPT users, so they're flowing in that direction. This is the number of visits per user per month, and that's growing. And then we have the number of queries per user, but per visit, I mean, and that's growing. That leads to queries, which leads to energy consumption when we take the energy per query, which hopefully is declining. The outflow shows that we're going to decrease the energy per query. And then we have the energy required, and the energy required goes into this value. And this is also balanced by the rate of usage of renewables. So this is the stock of the production of renewable and nuclear energy. So the nuclear energy is growing, and the renewable energy is growing. So then that reduces the share of fossil fuels, and then that leads to CO2 production going down. And this is the carbon footprint. The carbon footprint may go up, but the production is going down. That's what we're actually looking at, is trying to reduce this production. And we have two levers that we try to use to do that. And the first one is, let's say the first one is down here in the bottom right-hand corner, and that is the pressure on AI companies, AI products and product builders to reduce their energy or make their systems more energy efficient. So this is like, as I said, the more energy used, the more pressure there will be to reduce that energy used. And so we have a lever that says we're going to influence this by putting political or policy pressure or some kind of pressure on the manufacturers of the AI products to reduce their emissions, reduce their energy per user, per query, I mean. And then And then we also have another lever, which is the renewables usage. And so up in the top left-hand corner, we have this idea of acceptable amount of CO2, and then we want to reduce that amount of CO2, and we do that by increasing the amount of renewables and nuclear energy. So that's the other lever. So we have two ways to do it, and to do the reduction in CO2 production. So that's some of the insights we get from the system dynamics model. So then we calibrated the model to the ChatGPT data, which was only up until 2025, and then we looked at the long-term projection into the future, and we felt that based on the information we had, we felt that the market saturation might occur somewhere around mid 2026 or 2027, and then we would see an equilibrium state where basically we'd reach around 92 megatons of CO2 production per month, and that would continue till 2032. And then we have these, as I said, these policy levers. So we have the first one is in efficiency pressure. And so we might have interventions like accelerated hardware and software performance per watt that is designed to efficiency. And we might be able to do that through sparsity, distillation, batching, caching, accelerators, and facility usage efficiency improvements. So those are some of the things that we could do to improve the efficiency of the algorithms and the hardware. And here's the influence of this pressure. So as I said, we have a moderate and an aggressive strategy, and basically the baseline is no pressure, so a flat line on the energy per query. And then with moderate pressure, we can reduce the energy by about 20% by 2032. And then with aggressive pressure, we can reduce it by around 30% or 35%. So that's the energy per query pressure. And then the next one is renewables. So the intervention is to increase the low carbon or carbon-free supply of energy that is feeding the data centers and the data center regions. And then the mechanisms could be purchase power agreements, sightings near nuclear and hydro, storage like battery storage, and time and use shifting, and grid-aware inference. So those are the kind of things we might be able to do to improve the renewables usage. And here's the pressure on renewables. And you can see that we have moderate pressure increases the usage by sort of exponentially by around 300%, and aggressive pressure gets it up to 700%. These sound like large numbers, but actually they're not really all that large because the baseline is so low in terms of the renewables we're using today that actually 700% increase in the current, based on the current usage, current renewables usage is really still not very much. But it is hopefully growing exponentially. Okay, so we want to combine these levers and look at the trade space. So we have a portfolio that combines efficiency and renewables for resilient abatement of CO2. And then we have hopefully an efficient frontier, which has budget and performance constraints. And I'll get into that a little bit more when I get into the systems engineering aspects of this project. And then we have a number of co-benefits. So we have things like latency, capacity headroom, and operating expenditure savings. So even by just reducing the energy, we can reduce the costs. So that's a benefit. And here's the results in terms of CO2 production per month for over the next 15 years or so. And we see that the moderate pressure leads to a reduction of about 35%, and the aggressive pressure leads to a reduction by about 60%. So anyway, so that's here's a dashboard we developed for doing these trade-offs. So we see we have this pressure coefficient here, and we set the pressure here in this case at five units, and that's fairly aggressive, and that leads to a 27% improvement, a decrease in energy requirements, and a 458% increase in renewable energy in 2032. And then this leads to a 48% reduction in CO2 by 2032. And we can set goals for these things and find the pressure required, or we can basically see if we set a goal of, say, 50% energy efficiency improvement, we can see what the CO2 reduction would be with that if we achieve that goal. So this is a dashboard that we can use to look at trade-offs. So some risks and limitations of this work, obviously. Limitations include that the calibration of data quality, and then there's regional energy factors that haven't been considered, and then of course, we're assuming breakthrough technologies in terms of improving efficiency, and obviously breakthrough technologies are uncertain, and you can't guarantee them. So that's quite a limitation on this approach. We have some mitigations of those risks. So, for example, we should be doing rolling calibration. So as we get new data, we should continue to calibrate the model to see if we can get better results. And then regionalization, we should try to regionalize the model so you can look at placing data centers where they're most efficient in terms of renewable energy. And then also tech watch scenarios for trying to monitor technology breakthroughs. The next steps for the system dynamics model is to integrate training into the carbon footprint, because we only talked about queries in this model, and to add cost and latency constraints. That's basically cost and performance constraints, and possibly expand to regional models so that we can look at the placement of data centers for possible future efficiency gains. One great thing about this model is it's reusable across many digital infrastructures. So, for example, the same structure could be used for cloud services, for internet search, for streaming, for inference APIs, and for enterprise software as a service. So we can just basically use the same model, swap out the reference modes and the factors, but retain the same basic blueprint and governance pattern for these other applications. And the goal, of course, is to accelerate uptake in these areas, and we can use the same basic causal loop diagrams and stock and flow diagrams and requirements libraries to do that acceleration of uptake and the reduction of CO2 across a lot of different technologies. So now I'm going to get into the systems engineering, and hopefully I'll show you how the systems engineering can be coordinated with the system dynamics model. So we have two projects for systems engineering. So obviously we want to make AI use less energy per query. And the goal here is to reduce the energy per query without slowing down the product or compromising its accuracy. Second project is to power the AI with cleaner electricity. And the goal here is to increase the share of low carbon power feeding the data centers and lower the CO2 per kilowatt we use. So in the first project, what's in scope? Well, we want smaller, faster models, which we might be able to do through pruning, compression, and distillation. And we want smarter servers. So we could do batching, caching, compiler runtime tweaks to achieve smarter serving. And then we have hardware choices and placement. As I mentioned quite a few times, we want to maybe improve the hardware and place the data centers in efficient places. And then we can also look at the cooling and the power improvements we could make at the data centers themselves for greater efficiency in the data centers. And then we have how we'll measure success. So we will look at energy per query, obviously, and monthly CO2 created, and the cost of the query per query. And then we'll have speed and accuracy constraints. So we want to reduce the energy, reduce the CO2, reduce the cost while still maintaining speed and accuracy. So that's sort of a constrained optimization problem here. And then there's risks and fixes. So if accuracy drops, we might want the ability to do a fast rollback, so we can go back to a previous configuration if we find that the new configuration doesn't work out. And then if we find slower responses, we might use batch sizes and routing and tune those to improve the response rate. And hardware delays, we might want to have the two vendor options to make sure that the hardware delays are limited. And the owners of this project, the overall owner is the platform engineering leader, and then the day-to-day leaders are the performance lead, the machine learning lead, and the data center operations lead. Now we'll get into project 2, that is power the AI with cleaner electricity. And what's in scope is power purchase deals with clean providers, choosing locations near nuclear hydro where possible, adding storage and shifting workloads to cleaner times of day, and routing work to regions with cleaner grids. So those are the kind of things we can do to improve the renewables and get cleaner energy. And then how we're going to measure success is we're going to look at the share of clean power serving the load. We're going to try to measure CO2 per kilowatt hour and monthly CO2. And then we're going to have cost constraints, the cost per megawatt hour, and the cost of delivering or the deliverability of the energy, which could be a constraint. So again, we want to increase the share and decrease the CO2 with cost constraints and deliverability constraints. And the risks and the fixes. So if the contracts or grid connections are delayed, we might want to diversify regions and use interim certificates if needed. And if power is curtailed, such as solar or wind, we want to add battery storage, for example, or spread the load across time and regions. And if we're uncertain about the grid and don't have necessary data on the grid, we might want independent verification, and we want to update the data regularly. In terms of owners, we have the overall owner is the infrastructure facilities leader, and then the day-to-day owners are the energy procurement officer, the site strategy officer, and the grid programs officer. So as a call to action, we want to embed energy efficiency requirements in LLM product roadmaps right now. And we want to stand up a systems engineering aligned system analytics blueprint and dashboard for decision support. And we want to institutionalize governance, reporting, and traceability for sustainability claims. Okay, that's my presentation. Thank you for your attention. And I'm open for questions and comments at this time.
Thank you, Ivan. That was really good. It really gets you thinking. I've got a question for you. You may have covered this already. I apologize if you have. But in your system dynamics model, what assumptions or how did you characterize the impact of AI on the evolution of technology? So there'd be impacts on possibly academia, the whole breakthrough technology, and just the improvement in efficiency. What is that role? How did you characterize that relationship? Because the AI has to help us help itself.
Yeah, I didn't actually look at the multiplier effect there,
Mm.
but what I did look at was the idea of integrating AI with workflows, so that basically we would have exponential growth in the number of queries that's created by the integration of AI into workflows. So basically, what I didn't look at, like you say, the multiplier effects of how AI can benefit society in those ways. But I did look at the idea that the more benefit, the more successful implementation of AI, the more likely we'll have more users and more usage of per user. So then, so that's basically the only things we modeled.
Okay, okay, I see. All right, I think we're a small enough group that if you have a question, please feel free to unmute and just ask your question. If you're not comfortable asking yourself, put it in the chat and I can read out your question for you. But yeah, the open floor, please go ahead and ask your questions or provide your comments.
I think Kai had a comment or a question.
Yeah.
I was getting ready to read my mind.
Oh.
Very naive questions. I didn't, very fantastic presentation, Ivan. Thank you very much. I didn't understand. Can you hear me properly? I'll try and speak up. At some point in the there were no page numbers, so I don't remember exactly where, but when you quoted the CO2 and either the projection to diminish or and you stated it, would that be Canada-wide? I don't know what the application or range was at some point, so I'm sorry that I can't give you more of the context, especially when I was wondering about that, but how did you usually?
Yeah, I just wanted to put 92 megatons per month is a large number that maybe we can't comprehend. We need some kind of anchor for it to understand it better. So what I did is I looked up the CO2 production per month for Canada, which was about 58 megatons per month. And I said, I just divided 92 by 58 and got 1.6. So that led me to the conclusion that the 92 megatons per month was 60% higher than the CO2 produced per month by Canada. In 2023, though, so it's basically the 2023 values of CO2 production in Canada. Does that help?
Yes, it does, because what I was wondering is with the projections you made and when you said that it would be a reduction by, depending on which aggressive or not
Yeah.
path we choose, would still mean that we actually overall increase by a lot. And I'm currently looking at Quebec's project to reduce to the level of 1990 by 2030 with the 37% reduction in carbon emissions. So it seems as if it's impossible if we use AI, whether we believe that it will multiply or not our efforts in making us more sustainable. I don't know. It just seems so self-defeating. That's what I felt, even with the prospects and the passes you calculated. Am I correct by saying that one way or another, anyways, it will always be increasingly?
Yeah, that's very interesting, Kai. One of the things that in our paper that we're trying to get published, we talk about something in the limitations about the side effects or the unintended consequences of these policies. So, for example, reducing carbon emissions might increase people's energy usage because they see that they're not hurting the economy, hurting the environment as much. So they actually just use more energy, which leads to basically the same result. And similarly, reducing energy requirements in the AI products might lead people to just use these products more, especially if they realize that they're not going to reduce any kind of performance from the AI. So basically, some of these policies and have sort of a balancing effect that basically, we're doing good things, which lead to more of the bad things.
Ivan, what do you think about regulations in the future? Do you think that there may be some regulatory enforcement so that we don't continue to consume more? Because I understand that your last point.
Yeah, I think the in terms of regulations, like I say, I didn't look at particular regulations, but I think I tried to approach that from the pressure idea. So basically, as we require more and more energy, there should be more regulatory pressure to become more efficient. And similarly, as we produce more and more CO2, there should be regulatory pressure to reduce the amount of CO2 by using more renewables.
Right.
So basically, the regulatory idea, I think, is embedded in this pressure idea.
I see. Okay. Yep, that makes sense. Yeah, because we see it now. I'm not sure what the delta impact would be, but anytime you do, for example, a Google search, you get the AI answer first, and you might be doing a simple search and not require that processing, but you get the processing regardless, unless you go in, and I believe you can and I haven't done this.
Yeah, that's actually an
Block that.
interesting point as well, Ivan, is that using AI it has an opportunity cost in the sense that if you use AI to answer your question, you're not using Google searches. So if you say get a good answer from AI on the first search and don't have to do 10 Google searches to find the right answer, maybe you're actually not doing so bad. Maybe if it saves just normal Google searches and normal work that would use energy and CO2 by doing it more efficiently through AI, there might be savings there that are hidden in our model because we don't consider the substitution effect.
Right. Good point. Any more questions? Please unmute and ask.
Ivan, I have a question. So did you use any consideration in your model about like any sort of regulations or mechanism that sort of mandate a large language model provider to meet their own energy requirements? That could be like more additional constraints on like having like some part of it from renewable energy sources. Then if they are responsible for providing their own energy, then they would just think deeply about like the efficiency and the impacts on their clients. How about a scenario like that?
Yeah, I think that's happening today. I think that I think there's a lot of these companies who are really seriously investing in energy production near their data centers, and I think they're actually they're not leaving it up necessarily to just energy producers normally. They're actually stepping in and trying to have more of a vertical market of energy and AI. So instead of having, getting energy from other people, they're getting energy from inside their own organization. But yeah, I think that again, another aspect of it that I think may be related to your question is the fact of transparency. So, for example, I think that that companies need to actually provide data on how much energy they're using and how much CO2 they're producing, and just the just the just the expression of how much of these things could influence people, influence companies to do better. So basically, I think one of the things that government could do is encourage or not encourage, but actually regulate transparency and make sure that the companies actually report on what they're doing in terms of energy efficiency, energy usage, and carbon emissions.
Thank you, Ivan. Very good presentation. Thank you.
Yeah.
Ivan, we have
Ivan,
another question here.
I'm sorry. I'm assuming that
Oh.
the changes that you are referring to will require a lot of training. And is this part of a model that you are proposing? Unfortunately, I missed the first half of your presentation,
well,
so I'm sorry
Good, you
if
could
I.
make it, Reza. Yeah.
Yeah.
That was part of the discussion, was that our model unfortunately focused completely on the operations or the queries that were driven or driving the AI usage and the CO2 production. But we didn't model the training process. I think though that maybe I'm wrong, but I think the training of AI might be a little more, there might be more data available on that. The costs of training, the amount of energy used in training. It seems to me there may be more energy, more data on that, and to some extent, I guess the idea is, they keep training newer and newer models, but it is sort of a fixed cost in a way, because it's not based on usage.
Thank you.
Ivan, we have a question here from James in the chat. I'll just read it out. Are you able to describe how extensive other AI stakeholder groups or interest groups have carried out their analysis research regarding AI's carbon footprint and any mitigation strategies that they are proposing?
Yeah, like I said, there is I did see a paper recently on something similar. I can't remember exactly what it was, but I know that I've seen papers on other products like cloud services and um, and data centers. So I know this is a hot topic, and I know there's other people looking into other aspects of it. I'm not sure if anyone else has done it quite the way we've done it. I think though that if James wants to contact me, I can get him in touch with these other authors that did this paper, and he can contact them and maybe get a copy of their paper. It definitely was highly related to this, and I think it had more to do with substitution effects and things like that. So,
Excellent.
anyways, but yeah, James, why don't you contact me after the meeting? You can either contact me through LinkedIn or through my email, ivantaylor@incosi.net, ivan.taylor@incosi.net, and or ivan@policydynamics.ca, and then you can. I'll get you in touch with the other people that I know of that are working in this area. There's actually in terms of cloud services, there's actually I think two or three professors in University of Toronto that have written a paper on this.
Good. Next question.
like to put a shout out to Mehdi. Hello, Mehdi. He and I are working together now on a project, and so it's good to see him.
Oh, good.
We just started working together, so I guess he must have found out about this presentation and showed up.
Excellent. Any more questions? No, going once. Going twice. No, okay. Well, thank you, Ivan. This was a interesting presentation, and I think we're all interested, maybe concerned, what direction things are going. It's an exciting branch of technology, but yeah, this impact is real, and I'm very curious.
Well, I think one of the things that this paper I was referring to by my other colleagues
Yeah,
was the idea that this is not a new situation. Every technology that comes along,
Mm.
there's a lot of panic about the impact of it, and so there's a certain amount of is this really any different from the past, or or is this just
Oh, very true.
is this just another technology that we're going to adapt to, and
Mm.
and it's not going to destroy the world.
Yep. Moving from horse and buggy to automobile,
Yeah,
and
yeah,
now going to autonomous driving.
yeah.
That's true. Very true. Ivan, do you know, have we set a date? Please remind me for the case study. Um,
I understood that next month we have Kifang presenting,
yes.
and then we're going to do in November our case study.
November. Okay.
Although we are intending to do a 4-hour case study, so
Yes.
it'll probably be on a Saturday afternoon or a Sunday afternoon or something.
Right. So please do stay tuned for that. So next week it'll be another presentation, a continuation from something we did, I think it was a couple of years ago. Kifang and Sergio had given us a presentation
Yeah, that's
on
next
that,
month, right?
on rail. That'll be next month.
Yeah.
Um,
And this case study that we're working on follows on from a presentation last month on programmatic risks. And the case study we're going to do is on the Ottawa light rail program.
so
That
this will be Ivan Taylor and Ken Cureton.
yeah, the Ottawa light rail program had a lot of programmatic risks involved in it, and they actually had some kind of a inquiry. I think it might have been an Auditor General inquiry into the programmatic risks of it, and so it's a very, very good case study.
It'll be a good one. Yeah, and as Ivan mentioned, that'll be probably a 4 hour long workshop. So a very interesting one to attend. So stay tuned. Take a look at the Nkosi Canada chapter website, and you'll see what our upcoming events are as they get opened up for registration. We look forward to everybody joining us for future presentations. Thank you again for joining us today, and thank you, Ivan. This was very good.
Yeah, and I'll post this on my LinkedIn page as well if anyone wants to connect with me on LinkedIn.
Very good. With that, we'll close for tonight. Thank you, everybody. Have a good evening.